In this physics video, we are going to talk about scalars and vector quantities. So let's get started. So I'm going to start off by explaining what scalar quantities are, then I'll talk about what vector quantities are, then we'll move on from there. So what are scalar quantities? Scalar quantities are physical quantities that can be specified only by magnitude. So what that means is, if you want to define a scalar quantity, you just state the magnitude and maybe you add a unit to it, right? And that's all you need to do. Because with the magnitude and the unit, you are okay. You can fully define what that quantity means and what it represents and the effect of that quantity. So for example, if I tell you that a particular object has a mass of, let's say, 20 kilogram, that's all you need. That's all you need to know, because with 20 kilogram, you have the information that this object has this amount of substance. So that's the mass, and that's a scalar quantity. Now let's look at another example, time. If I tell you that it took 5 seconds for a particular task to be completed, that information is sufficient to tell how long that event took, right? And that's all. So scalar quantities are things you just define by magnitude, and then there may be units to them like kilogram or seconds and all of that. But the idea is only the magnitude is enough to define a scalar quantity. And if you want to combine scalar quantities, you combine them using the rules of arithmetic and ordinary algebra. In other words, if I told you that an object A has a mass of 20 kilogram, and I told that an object B has a mass of 10 kilogram, and I asked what is total mass, you just simply add the two together and the total mass will be 30 kilogram. So when you want to combine scalar quantities, you just apply basic rules of arithmetic and you are fine. So what are the examples? We have mass, time, distance, speed, temperature, energy, pressure, and so on and so forth. Now let's contrast that with vector quantities. What are vector quantities? Vector quantities are physical quantities that can be defined by both magnitude and direction. In other words, magnitude is not sufficient to define a vector quantity. A vector quantity. If you don't define the direction of a vector quantity, that is incomplete. You can't fully tell the effect of a vector quantity if you take away the direction. Now, the question you may be asking is, what do we really mean by direction? So direction means that the direction in space, like in the real world, in space. So the direction we're talking about now is the direction in the physical world, in 3D space, right? Although in most cases in physics, you'll be given direction in 2 dimensions. The assumption will be that you have an object moving on a plane surface, but even though you have the direction in 2 dimensions, you can still define it in terms of 3 dimensions. So when you hear the word dimension under vector, what it means is the path it took, or the path that particular quantity is expressed in a physical space. So that's what direction really means. Okay, so let's now break it down. Magnitude and direction. So let's pick an example. So let's say you have a particular let me take an example of a vector quantity which happens to be force. So force is a vector quantity, right? Now let's say you have a block of wood, and I told you that I applied a force of 50 Newton on this block. If I don't tell you direction in which I apply this force, it will be unclear as to the effect of the force, because the direction of the force will determine the effect on that block of wood. If you apply the force from the left side to along the left side of the block, what that means is you expect that the block will move to the right. If I apply that force at the bottom, 50 Newton, right? The direction of that block will be entirely different from if I applied it on the left, and so on and so forth. So what this means is vector quantity, defining just the magnitude, which is 50 Newton, right, is not sufficient to tell the impact of that quantity. To really know the impact of that quantity, you must tell you must specify the direction. So the direction could be something like north. So let's say this is your reference point, right? And I said, oh, I applied this force in the northward direction. Now it clearly tells the line of action of that quantity. And that can help you know the effect of that quantity, because if you apply it upward, you can tell what's in where that object will go to, right? Because you know the direction. And it can help you calculate many other things, right? So if you don't specify direction for a vector quantity, you have not fully defined a vector quantity. So the direction is critical in defining vector quantity. Now, let's take a look at another example. So let's say I told you, let's say somebody happens to be at point A, right? And I told you that the person moved a distance of 20 kilometers, right? Now, if I told the person moved covered a distance of 20 kilometers, can you tell where the person will be right now? The answer is no, you don't know where the person will be. Because if you just tell me 20 kilometers, what you've just specified is distance. You've told me distance, and distance is a scalar quantity. Now, if you want to know where the person would be, then you need to go beyond telling me the magnitude. You need to tell me the direction. And now, if you tell me this person moved east, let's say this is a reference point, and I told you this person moved east, and the person covered a distance of 20 kilometers. Now, you've given me two information: 20 kilometer east, right? Now, this represents direction. And because you've told me direction, I can predict where the person would be right now, because I know the distance, I know the direction, that I can tell where the person is. Now, by adding this direction to this distance, it becomes displacement. It's no longer distance. So the information I now have now is displacement, no longer distance. So essentially, what distinguishes a vector quantity from a scalar quantity is just direction. If there's a direction to a magnitude, then it becomes vector. Although not all quantity will have direction. Some quantities, it doesn't make sense to add a direction to it. For example, you can add direction to time, you can add direction to mass, and so on. But there are certain quantities that if you add direction to them, they turn to vector. If you remove direction from them, they turn to scalar. Another example is speed. If you just tell me the speed of a car, how fast the car is moving, you've just told me the speed, and that's a scalar quantity. But then if you tell me the speed and the direction in which that car is moving, then you've told me the velocity. Because now with the velocity, I can predict where the car will be at a given point in time, because I know the speed and I also know the direction the car is going. And that makes it a vector quantity. So now the next thing is, how do we combine two or more vector quantities? You don't combine them using basic arithmetic rules. You combine them using geometry, or using what's known as vector algebra. So we're going to explore that concept. How do we combine two or more vectors? And that's the next topic. That's what we're going to talk about after this slide. So let's talk about how we represent vector. Then we'll talk about how we combine vector. Let's talk about vector representation. How do we represent vector? As we said earlier, you need to define two things: the magnitude and the direction. So for the magnitude, we represent with a line. So if you have a line of this sort, this line represents the magnitude. When you draw a vector, you draw it to a particular scale. So what that means is, let's say this vector represents, let's say, 10 Newton, for instance. Now I could say, okay, let's maybe 1 centimeter, let's say, represent 5 Newton. So that's just what you can choose any scale you want. But basically, when you see a vector being drawn, the length of that vector represents the magnitude. Then what about the direction? The direction is defined by an arrow, by an arrow head. Now this arrowhead represent the direction that this vector is the line of action of this vector. So if this represents 10 Newton, and let's say this represents 10 Newton along a particular path, right? This path could be a particular degree northeast, right? Maybe 45-degree northeast or whatever unit direction you specify. This could represent another vector whose length is 20 Newton. Now, if you notice, they have the same direction, but then the magnitude are different. This one is twice the magnitude of this other vector. If this vector A and this vector B, so this is twice. So what that means is you draw the length of the line gives you an idea of the size of the vector. The arrowhead gives you an idea of the direction of the vector. So this is how vectors are generally represented in books and in computation and so on. So if you have two vectors that are parallel to each other, right? What that means is they have the same direction. That's what it means. So parallel vectors means the same in direction, but they could be different in magnitude depending on how long they are. If they have the same length, that means they are the same in magnitude. So basically, this is how you represent vector. So now let's talk about how we combine vectors. Let's talk about resultant vector. Now, what exactly is resultant vector? Resultant vector can be seen as you can you can conceive it as the sum total of two or more vectors, or better still, you can see it as the combined effect of two or more vectors. So what this means is a resultant vector is a single vector that would have the same effect in magnitude and direction as two or more vectors acting together. So if you have the following, so let's say I have two vectors, one acting upward. So let's say this is 10 Newton, and I have another vector acting along the x-axis, and this time around, let's say this is 20 Newton. Now the question is, what would be the combined effect of this vector? In other words, if you have this block, and imagine that this block, there's a force acting, a 10 Newton force, right? Acting upward, and you have another force. Let's say somebody's pushing this block along this direction, 20 Newton. And I ask you, what is that single force that will have the same effect as these two forces? That is, if I were to apply a single force on this block, what would be that single force? What would be the magnitude of that single force? And in what direction should that single force act such that it will create the same effect as these two forces acting together? So that's what resultant force is all about. So it helps you to know how to take two or more forces and combine it into one single thing. Like telling you, if you combine these two or more forces, what is that single vector? What is that single vector that would have the same effect as all of these vectors acting together? So now, how do you get how do you compute resultant vector? So this is what we're going to be talking about going forward. How do you compute this resultant vector? But before I go into that, let me just give you an idea as to why we are interested in resultant vector. Why are we interested in resultant vector, and why does it really matter? So imagine you have this rocket, or let's take this example of a drone. Not Let's take the example of a drone. So you have this drone, and this drone is hovering. Now this drone is experiencing. Let's imagine two forces, right? There is this force of gravity on it, the weight of that drone, and let's say there is wind blowing along this direction. So there is wind of a particular force. So let's say Fw, the force of wind. So let's say wind is blowing by the side, that is the direction of the wind is blowing westward, right? Now, what would be the resultant of this force acting on this drone? If you can calculate the resultant vector, or you can say resultant force on this drone, that can help you figure out a particular action to be taken that may cancel out these two effects. Because if, for example, I get to know that the resultant vector is somewhere along this path, right? Let's say I ended up having this as my resultant vector. What this means is if I can produce a force that goes in opposite direction to this resultant vector, and that force has the same magnitude as this resultant vector, but the direction is opposite. If I can make this drone produce a force that goes exactly in opposite direction to the resultant vector, I'm going to end up canceling out this wind effect and this um, force of gravity on the drone. So resultant vector helps you to take all these vectors acting on a particular object, turn everything into a single vector, and then use that information for something else. So that's one of the reasons why we calculate resultant vector. So now let's take a look at the method for calculating resultant vector. Now, before I go deep into those methods, I want you to take a look at how we represent two or more vectors. So let's say you have vector A acting in this direction. So let's say this is vector A, right? And let's say this is direction of this vector A. And let's say we have another vector. So this is vector B. And vector B is acting in along this direction. If I ask you, how can we represent these two geometrically? Because if I want to get a resultant vector, I need to combine them in geometrically. Now, how can I combine them? So this is how you combine them. You take the first one. So let's say you are looking for the sum of the vector sum of A and B, right? This is like a vector sum. It's not you don't add them in an ordinary way. So let's say this is, for example, 10 Newton, and let's say this is, for example, 20 Newton. You don't just add them up and get 30 Newton. No, you don't have vector that way. So how do you get the vector sum of this? You get it. Let's look at how we represent it geometrically. So you represent geometrically by taking the A. The A will be here, right? Then once you end with the A, you continue with the B. That is, you first draw vector A, then you start from the head of this vector A to draw vector B. And that means you go this direction. You make sure that you go in the same direction as this vector B, right? Then you stop once you've drawn the length of vector B. So this is vector B, right? So the resultant vector is the vector that runs from the very beginning to the very end, to where you actually stop. So this is the resultant vector. So this R is actually the resultant vector, is the single vector that will have the same effect as these two vectors acting together. So this is how you geometrically represent two vectors acting together. So if there are three vectors, the same rule. After you draw the second vector, you continue from the head of this second vector and draw the third and keep going that way. So that is how you go about drawing this. So, but what if I want to subtract? So let's say I have this, I want to subtract. So let's say I want to take vector A minus vector B. How do I go about it? Well, when dealing with negative number means you change the direction. So if I have vector B to be this, then minus B, vector of minus B will be, we have the same magnitude as this, but the direction will change. So what that means is, instead of this arrow pointing upward, the arrow will point downward, but the length of this two will be the same. It will also be 20 Newton, but this time around, the direction is going to change because now you are going in the opposite direction. So if you have this, if you want to calculate A minus B, what that means is you're going to get the vector A, which is this, right? Then to get the to minus b would be you going in the opposite direction, going in the opposite direction. So the resultant vector will be something like this. So this will be the resultant vector. So this is R2. So this is the if this is A, this is minus B, and this is the resultant vector. So this is basically how you draw two or more vectors acting together. So now that we've sorted this out, now let's talk about how we actually calculate resultant vector. Let's start with two vectors acting together. So how do we calculate that? Okay, there are two methods that are commonly used. One of them is known as parallelogram method, and the other one is the triangle method. So let's start with the parallelogram method. So let's say you have two vectors, and these two vectors they meet at a particular angle. So let's say the angle is theta. So let's say this is vector A, right? And let's say this is direction, and let's say this is vector B, and let's say this is the direction, right? Now, this parallelogram law of vector states that the resultant vector is the diagonal of the resulting parallelogram. So imagine we extend this, and imagine we extend this, right? Let's imagine that we extend this out to form a parallelogram. This parallelogram law of vector states that the resultant vector is the diagonal of the resulting parallelogram. So if you think about it, what that means is the this represents the resultant vector. And if you can calculate this diagonal, you've got the resultant vector. And this rule applies to a case where you have two vectors acting together. So that is what the parallelogram law of vector states. We have two vectors A and B acting together, and let's say they meet at they intersect at a point, right? The diagonal of the resulting parallelogram is the resultant vector in magnitude and direction. Magnitude means the length of this the diagonal will be the magnitude of the resultant vector, and the direction of this diagonal will be the direction of the resultant vector. So that's what the parallelogram law of vector states. So let's look at the second method, which is that if two vectors A and B are inclined at angle theta to each other, there is the resultant force C is given by this. Okay, let's look at what that states. So let's say I have this vector B, right? And I want to add vector A to it. Don't forget that if you want to add vector A to it, you can just continue from here. So this represents vector A, right? Is the same direction and magnitude. Now the triangular law of vector states that the third side represents the resultant vector. Now it represents the resultant vector in both magnitude and direction. So what this means is this C represents the resultant vector. And how do you calculate C? So this represents the angle of intersection. They are inclined to each other at angle theta, right? Although you can represent it in a the angle could be anything, right? So the question now is how do we calculate C? So you can calculate C using a cosine rule. There is this cosine rule that can help you compute this length, given you know these two sides and the angle between them. So and that is actually equal to C raised to power 2 equals A raised to power 2 plus B raised to power 2 plus 2AB cos theta. So this is basically how you calculate the resultant vector when you have two vectors acting together. We're going to talk about more. We're going to solve some questions based on all these concepts, so that you'll be able to understand better. Now let's talk about another concept, which is known as components of a vector. So how do we take a vector and break that vector into components. So let's talk about that. Every vector can be broken down into components. So what that means is you can take a vector. Let's say you have this vector, right? And let's say the units, let's say this vector represents 4 Newton, right? Now you can take this vector and break it into components. You can say, what is the effect of this vector along several axes? So let's say in this case, we're already dealing with two axes. Let's say this is the origin and we're dealing with x-axis and y-axis, right? So this is y-axis, this is the x-axis. So let's say I ask you, what is the effect of this vector, or let's be more specific, of this force along this axis and along this axis? Now, what does that mean? It means what is the component of this force along this axis? That's basically what I'm asking. And you'll be asking, why do we need to break things into components, and what does it really imply? So what it implies is this. So imagine you have this block of wood, and imagine you are pulling this block of wood along this direction, not horizontally, not vertically. You are pulling it at an inclined angle. And let's say you're applying a force of 4 Newton. Now, you are trying to do two things, right? This force you're applying has two effects. It has a kind of horizontal effect and it has a vertical effect. Now, what that means is this force you're applying is trying to do the two things. It's trying to drag this block horizontally, and it's also trying to pull this block upward, right? It's trying to pull this block upward, and it has two effects: horizontal effect and vertical effect. So if I ask you, what is the horizontal component? What I'm saying is, what exactly is the force acting on this block horizontally? If you take this force and you try to resolve it into two parts, in other words, try to uh, uh, break into two components, what will be the horizontal component and what will be the vertical component? So that is what we mean by component of a vector. It is basically the projection of a vector on axis. So that's what it means. It's more or less like you reversing resultant vector. So think about it this way. If I have two vectors and both vectors are on the horizontal axis, so let's say this is 2 Newton and let's say this is 6 Newton, for instance. Let's say this is 6 Newton and this is 2 Newton. Now, if I ask for the resultant vector, it will be somewhere like this. I mean, somewhere along this line, right? That will be the resultant vector. Now, what component of vector is telling you is, if you know the resultant, right, can you guess what the horizontal component and vertical component is? In other words, can you guess those two components that gave rise to this resultant vector? That is exactly what we mean by component of a vector. It's like you taking this single vector and trying to break it into two or more. Now, what I mean more is this: if you have three axes, if you are dealing with x, y, and z axis, then it's three. But if you're just dealing with a plain surface, then it's just two components, right? So that is basically what a component of a vector is. Just the effect of that vector on a given axis. And in most cases, you'll be dealing with two axes, x and y. Now the question in your mind is, why do we need to break a vector into components? Does it really matter? Yeah, it does matter, because if, for example, this object weighs 6 Newton. Now, you may want to know if this force will lift this object. To know if this force will be is sufficient enough to lift this object, you need to find the vertical component of this force. If it turns out that the vertical component is very small, so let's say it turns out that this vertical component is 3 Newton, for instance, This 3 Newton is less than the weight of this object. So because of that, this force will not lift this object. It may drag it horizontally, but it will not raise the object upward. But let's say it turns out that this weight, the weight of the object is 1 Newton. It means what will happen is the object may end up flying in space because of the application of this force. So resolving a vector into x and y component helps you know the effect along those axes. So that's the essentially why you we resolve vectors. So now let's talk about resolution of vector. So what's resolution of vector? It's just the process of finding a component of a vector. So whenever you hear the word resolve this vector or resolution of vector, it's just that process of you finding a component of a vector. The component is just any of this value, right? Any of the value along the axis. But that process of figuring out those values is what we call resolution of vector. So we're going to talk about let's talk about how we resolve vectors. So this is how you resolve vectors. So let's say you have a vector like this. Normally, you'll be given, let's say this is the y axis and this is the x axis. And let's say you have a vector and let's say this is 30 degrees, right? And you have a vector of 40 Newton, a force of 40 Newton. And the question is to resolve this 40 Newton into x and y components. So how do you go about it? Here, you need to apply some concept in geometry. So I'm going to walk you through some of those concepts in geometry. So the first thing I need to explain is this concept of let's look at this a right angle triangle. So for a right angle triangle, let's say we call this the hypotenuse, right? So this is hypotenuse H. So let's say given that this is the angle, so this is angle theta. This is the side opposite is theta is the opposite, right? The side that is at the base of this angle is known as the adjacent, and this is the hypotenuse, right? Now, from trigonometry, sine theta, sine of this angle is equal to opposite divided by the hypotenuse. So the opposite is essentially the hypotenuse times sine theta. So let's talk about cos. So what about the cos theta? Cos theta is adjacent divided by hypotenuse. So what is the adjacent? So let's say you are told to ask to compute for the adjacent. The adjacent will be the hypotenuse times cos theta. So these are the two formula you have to take note of. Very, very important. So what about another concept known as Pythagoras theorem? So let's say you don't know the angle, but you want to look for any of the side. The hypotenuse square, the square of the hypotenuse is equal to the square of the opposite plus the square of the adjacent. So this is the Pythagoras theorem. So these are the concepts you have to take note of because they'll be very important to resolving this vector. So let's see how we can resolve this vector. So this is how to think about it. So if you have this line representing the original vector, try to see this as a rectangle triangle. Just imagine that this is a rectangle triangle where this is angle 90 degree. This is the angle theta, right? And now we are looking for this particular side of the right angle triangle. So what is the side of the right angle triangle? This is the adjacent. It's adjacent to this angle. And once you are looking for the adjacent side, you use this formula where you can. So let's say this is fx and this is fy. So we can say that fx is the adjacent, which is equal to the hypotenuse, which is 40 times cos of the angle theta. So if you solve this, you're going to get 34.64 Newton. So what about the Fy? The Fy is the vertical component, and because the Fy can be projected to this, because this is equivalent to this, right? They're in the same direction. So you can just take this to be this side. And if you do that, it means this is also Fy. And now this Fy is the opposite to this angle. So you can simply see it as you can simply apply this formula here where you have opposite is hypotenuse, which is this times sine theta. So what's the hypotenuse? The hypotenuse is 40, then times sine theta, which is sine 30, right? And that becomes 20 Newton. So this is how you resolve a vector into the horizontal and the vertical components. So now let's talk about how you combine three or more vectors, because so far we've talking about getting the resultant of two vectors. So what about three vectors, four vectors, five vectors? How do you go about getting the resultant vector? So that will be the last concept that we'll be talking about before we start solving real questions regarding scalar and vector quantities. So let's take a look. So let's talk about how we look for resultant vector of three or more vectors. Okay, so let's say you have the following. So let's say this is the reference point here, and you have a vector acting along this direction. So let's call this vector F1. So let's say you have another vector acting along this direction. So let's call this F2. And let's say you have another one acting along this direction. So let's call this F3. So the question is, how do you determine the resultant vector of these three vectors acting together? So this is the strategy you use. Let's break it down this way. So what you want to do is this. You have your table. So this table will have the forces. So this will be F1, and this will be F2, and this will be F3. As many forces as you have, you just write them out here, right? So the next thing you want to do is you want to define the angle. What's the angle to the horizontal plane? In other words, the angle to the horizontal axis. So let's define this to be the axis. This is the y-axis, and this is the x-axis. So the horizontal, the angle to the horizontal is this, which is theta. So let's call it theta 1. So this will be theta 1. So for this other one, it will be theta 2. It will be theta 2 as follows. So this is theta 2. And for the third force, the angle will be theta 3 as follows. So theta 3 as follows. So what I want to do is to write everything out here, theta 2 and theta 3. So once you figured out the angles of those three forces to the horizontal plane, the next thing you want to do is to determine the components. So you want to calculate the horizontal component. And you also want to calculate the vertical component. So this is the vertical component, right? So now for the horizontal component, what you want to do is you want to use the following formula, which is for the horizontal component, you simply take F1 cos theta 1, F2 cos theta 2, and F3 cos theta 3. For the vertical component, just take F2, F1 rather sine theta 1, f2 sine theta 2, and f3 sine theta 3. So this represents the total. You add everything up. The total of all of this will give you your total horizontal component. Let's call this fx. And the total of this will give you the total of your vertical component. So let's call this fy. So your final resultant vector is equal to the square root of fx squared plus fy squared. So this represents the resultant vector. But then note that the resultant vector, you can represent this f of x, this f of x can be represented like this, and f of y can be represented like this. So basically what you're looking for is just this resultant vector here. So which, if you think about it closely, what I've just done is I've applied Pythagoras theorem here. So which is r squared equals fx squared plus fy squared. So this is basically how you calculate the resultant vector of 3 or more vectors. So we're going to solve an example later on, but this is just to give you the formula and the tools you need for what we are going to be solving very soon. Okay, so let's now recap what we've done so far. So we've talked about what scalar and vector quantities are, and clearly vector quantities are quantities that have magnitude and direction. Scalars just have magnitude. There's nothing about them that indicates direction. Then we also talked about how we represent vectors. You use line to represent the magnitude of a vector, and the arrowhead tells you the direction of that vector. And we talked about how we combine vector. The combination of vector is known as the resultant vector. If you combine two or more vector, you get the resultant vector. And to get a resultant vector of two vectors acting together, you can use the parallelogram law vector, or you use the triangle method. Then we talked about resolving a vector into component, and we talked about how you can look for the resultant of three or more vectors. So now let's solve some questions. Let's concretize what we've learned, and let's put everything together. So I'm going to take some questions from the UTME past question and also from wide past question, so that we'll be able to solve more interesting questions. So let's take a look at it.